really happy that all of you could join us. And I want to start off by thanking Mike and Alyssa Canastracci and Alyssa Johnson for all the help and heavy lifting that they did to put this webinar series together. And a big thanks to our presenters who put a lot of thought and effort into the material presented at the workshop back in 2021 and to the presentations that you'll hear about today. So just to give a bit of an overview, this workshop, which you can see the title on your screen, was held in May of 2021. Its planning was started before the pandemic. When the pandemic came on and everybody was sent home, we decided we wanted to move forward with the workshop, and so it was held virtually. And even though it was virtual, we attracted over 200 registrants. And the goals of the workshop were to identify poorly understood or misrepresented processes in the Pacific Ocean that are relevant to global climate and weather models. Additional goals were to review the findings of recent process-based diagnostic studies, and then to envision process studies that could further advance model improvement. And a fourth goal was to determine which observations from process studies might be sustained and become part of the redesign of the Tropical Pacific Observing TPOS 2020 effort. Throughout the workshop, one of the overarching themes to emerge was the need for a really sustained whole column sampling approach to advance process understanding and model improvement. And by whole column, we really meant that we need to observe and measure the atmospheric boundary layer and the upper ocean mix layer and the layers above and below those interface layers as a whole system. And so one of the advantages of hosting this webinar series now in 2025 is that we can say what has happened since then. And so this overarching theme to emerge from the workshop was actually parlayed into the US CLIVAR supported Airsea Transition Study Group, and the report for that was published last year. The workshop participants also highlighted the need for short-term process studies to observe small-scale processes at resolutions that are really finer than those resolved by current sustained observing systems. And the regions most cited as needing process studies were the Eastern Pacific upwelling regime, as well as the eastern edge of the warm pool. And there is a current ongoing effort to develop plans to go into the field as part of the TPEX, the Tropical Equatorial Pacific experiment, which is currently, the aim is to go out there in 2026 to 2027. So we're very happy today to have the list of speakers that Aneesh will be introducing in a few minutes to sort of give us an update on some of the thinking that was discussed at the workshop. And also, I think we'll hear updates on how our thinking has evolved since then. So I will hand it over to Aneesh.
Thank you, Charlotte. And thanks everyone for joining us. We have 4 really great speakers lined up today. We'll start with Dr. Yosuke Fujii from JMA MRI. Dr. Fujii is a scientist who's interested in ocean prediction or coupled ocean atmosphere prediction, ocean physics, data assimilation, and ocean observing system evaluation. Dr. Fujii is also the lead of the UN Ocean Decade project called SYNOPS, Synergistic Observing Network for Ocean Prediction. And Dr. Fujii led this variations article. Dr. Fujii, Yosuke, whenever you're ready, we can start. Thanks.
Yeah, thank you for your introduction, Aneesh. And hello everyone, I'm Yosuke Fujii, working at the JMA, Japan Meteorological Agency Meteorological Research Institute. And thank you for giving me this opportunity to introduce our article on US CLIVAR Variation. And this article reviews 3 studies on the observation impact on tropical Pacific observation using adjoint sensitivity. So not only I, also Ariane Verdi in Script Institution of Oceanography and Shuhei Masuda in Jamstech, and several other people contributed to this article. So first of all, I would like to explain what is adjoint sensitivity. Here J is a certain diagnostic function for some targeted phenomena, and this partial derivative represents the sensitivity of the diagnostic function to model variables and t. And here we substitute delta x e plus 1 as a target linear model, a tangent linear model. Then we get this the second equation. And here we use the definition of the adjoint operator. So the model operator M move here and change it to the adjoint model. Finally, we get the last equation, and this equation indicates that the adjoint model propagates the sensitivity. For example, we have one motor at a certain time, so we can trace the course of the one motor backward in the time using the adjoint model. So we may find that subsurface water warming causes the surface water warming data. Thus, adjoint model calculates the backward propagation of the sensitivity or influence of model variables on a certain diagnostic function like this. Next, please. And the adjoint sensitivity is used in science in several ways. First, it is very essential tool for data simulation. It is used for 4D bar system, the analysis, and state estimation to reproduce the data misfit to reduce the data misfit between the model and observations. Second, machine learning also uses adjoint sensitivity in the same way as in data simulation. Third, adjoint sensitivity can be used for observing system evaluation and design in many ways. And finally, it is useful to explore the scientific mechanism of a specific event or to investigate predictability. And next, please. Then, as an example in data simulation, I introduced the JMS Oceanic 4D bar system for seasonal forecasting first. The system had global area and 1/4 degree resolution, but the 4D bar analysis performed with the lower resolution model. And this system had 10-day data assimilation window and assimilated observation data in the last 5 days. The cause of the data misfit between the model trajectory and observation data are expressed by the adjoint model, and the increments in the first 5 days are adjusted based on the sensitivity information. And ensemble members are calculated from adjoint sensitivity obtained among the 4D bar analysts. Then this figure demonstrates that 4D bar predict the tropical instability wave or TIW much better than 3D bar version. And next, please. I would like to introduce tropical Pacific Ocean state estimation on typos generated by Ariane Verdi, Matloff, and Bruce Conrad. There are 1/3 degree resolution version, typos 3, and 1/6 resolution version, typos 6, and they use overlapping 4-month assimilation window. The oceanic 4D bar result with long data assimilation windows like typos is called ocean state estimation. There is no artificial heat, cloud, and momentum sources in the middle of the assimilation window in ocean state estimation. Therefore, they are often used for the budget analysis. As Verdi et al. 2023 down. Then, satellite arithmetry, OISST, and Argo, CTD, and XPT are assimilated through 4D bar in T-percent. And here, time warning data are not assimilated, so warning data can be used as independent reference data. This slide shows the improvement in T-post 6 over T-post 3, and this figure shows SST snapshot in T-process 6. Here, you can see the typical instability wave or TIW in the equatorial Pacific. And although T-process 3 have not represented TIW well, T-process 6 clearly resolved them. Then, this figure compares the zonal current speed at 200 meters along around 140 degree and 125 degree west. You know, the amplitude of zonal jet increased, and the steer jet around 5 degree north and around 5 degree south are better estimated in T-process 6. Then, this slide shows the result of adjoint sensitivity analysis with T-process 6. The cause of one SST in the Nino-3 region was examined with the adjoint model of T-process 6. And this figure showed the snapshot of the sensitivity of SST in Nino-3 on December 2015 with general wind stress and general wind stress perturbation 60 days earlier. And this figure indicates that downward turbulent wave excited by westerly wind anomalies can reach Nino-3.4 region in 2 to 3 months. Then this is the Hofmüller diagram of the sensitivity along the equator. And you can see the wave-like propagation related to TIW here. The current speed is constant with the observed TIW. And the sensitivity also indicates that the magnitude of SST warming depends on the meridional extent of the westerly wind anomalies. I introduced another ocean state estimation, SDOC, generated by Jamstack. And this is the data set for the period from 1957 to 2022. And the fall estimation period is used as the assimilation window. So there is no artificial sources of heat, bulk, and momentum in the data set for more than 60 years. In addition, the stock effectively represents the long-term temperature variation in the deep layer. And you can access the data set from this web page. And then Jamstack investigated the algo data impacts on the basin scale warming in SDOC. They estimated the sensitivity of the heat content in the whole Pacific basin to the temperature field 10 years before using the adjoint model. Then, in order to represent the feasibility impact of algo flows, the sensitivity is multiplied by the square root of the climatological variance and averaged over 0 to 2,000 meter depths. And the result is shown in this figure. You know, relatively high impact regions exist along the equator in the South subtropical region, the Western North Pacific subtropical region along 30 degree north and north of closure extension, west of 170 degree west. And next, please. Then, in order to show the effectiveness of optimal algo array design, impact for following two algo array design are compared. The first one is the control case, in which both are regularly deployed every 3 degrees in both latitude and longitude. And the second one is the optimal case, in which both are deployed 1,653 locations with the high visibility impact, as shown in this figure. And the total number of the locations are the same here. And we estimate that the total value of the observation sensitivity for the optimal case is 1.21 times larger than that of the control case. Thus, appropriate design of the algo array may improve the accuracy of the basin scale warming estimation. And I would like to introduce the array mode in the JMS operational system. You know, analysis error covariance of a variational method is represented by the inverse Hessian of the cost function. And we precondition the Hessian by the square root of B. then the eigenvector of the precondition Hessian are equivalent to the right singular vector of the matrix and reflect of this matrix R square R H M square B. So then this matrix is reflect the model error growth characteristics and also observation operator H. And the leading eigenvector represents the error pattern that observations effectively induce in the analysis. Then, approximate leading eigenvectors are regularly calculated in the JMS CLIVAR system for the ensemble member generation. And the vectors are the same as the reduced rank array mode used in Moore et al. 2017 and 2021. Next, please. And this figure shows the array mode for January and July 2013. This is the pattern of temperature at 100 meter depth. You know, the pattern of the array mode are different for different assimilation cycles. But a coherent signal can be seen in the equatorial Pacific, western boundary current region, etc., indicating high observation impact in those areas. And these signals are likely to reflect unstable modes of the ocean model. In addition, peak of the signal away from the equator in the eastern equatorial Pacific indicates the importance of equatorial observations in this area. And finally, next please. And finally, I would also like to introduce the Synops flagship OSEs. You know, Ocean Prediction Center are responsible to provide information on observation impact to sustain and improve the ocean observation network. Therefore, Synops is launched as the United Nations Ocean Decade Project in order to appeal the ocean observation impact. Synops is currently implementing the flagship OSE, which is collaborative coordinated observing system evaluation experiment, or OSE. And this figure shows the impact of satellite altimeter and algo data on the SSH field in the various ocean prediction systems. It is natural that altimetry data has impact on the accuracy of the SSH field. Adding algo data also improves SSH field faster in the whole system. And Synops also plans to evaluate the impact of the Pacific observations using the OSE results under the collaboration with the TPOS community. And next, please. And here I summarize the presentation. First, joint sensitivity is used for 4D data estimation in JMA and ocean state estimation, such as TPOS and stock. And modeling data are likely to be effective to improve these estimations. Second, joint sensitivity is a potential tool for evaluating and designing ocean observing systems. The joint sensitivity study with TPOS 6 demonstrates the importance of wind stress observations along the equatorial Pacific and for its forecast. And the joint sensitivity study with stock and the other mode of JMA system demonstrates the importance of east observation data in the tropical Pacific. Third, UN Ocean Decade Project Synops is now implementing the coordinated OSE study to evaluate the observation impact, which are common to most prediction systems. And then Synops plans to collaborate with the TPOS community to evaluate the equatorial Pacific observing system. Next, please. And that's all. Thank you for your attention.
Thank you, Dr. Fujii.
Thank you.
Any questions for? Oh, Billy, go ahead.
Yes. Good morning. Thank you, Yosuke. That was very interesting. I have a question about the adjoint method and the tangent linear method, and that is, how long can you carry that linear analysis either forward or backward? And does that give information about the physics that are going on? In other words, in some locations or for some processes, you could expect that a tangent linear method would be good for a long time, and in others, it might only be good for a short time. And so I guess what I'm asking is, do we get additional information about the dynamics from the tangent linear method?
Yeah, question. So first of all, however we can use adjoint, it depends on the model and also, usually we use ocean adjoint, not coupled adjoint. So if the coupling gas interaction is very important, we cannot consider it the ocean adjoint. So it's this. We cannot do the long adjoint sensitivity study. But on the ocean, we can backtrace the cause of the any phenomena to more than 1 year or but it's difficult to answer. So, but adjoint is basically based on the ocean physics. So, using the adjoint method, we can understand the physics and we can understand how can I say? Anyway, we can we can investigate the physical reason or dynamical reason to the phenomenon. So I'm sorry, I cannot answer well. But yeah.
Hey, thanks, Vinny, and thanks, Yosuke. Anna, do you have a quick question while we transition to Gary?
Yeah, thanks. Hi, thanks. I just had a quick question about the TPOSI 1/6 having such a better undercurrent than the 1/3. Was wondering whether there was any linkage of that with the adjoint, or whether there was a change in viscosity, etc., or whether it was just purely resolution.
I'm not sure, but probably, basically they first change the resolution and maybe, they need to change some model parameters to make the model good. I think the resolution of 1/3 and 1/6 has some characteristic change. So AD resolving or AD is not resolving. So probably they change some parameters of model, but I'm not sure. So I need to ask Verdi, Dr. Verdi.
Yeah. Matt is online. Matt, do you have a comment on that?
Yeah.
Briefly, it's primarily resolution. It was 1/6 from 1/3 to 1/6 horizontal, and the vertical was increased a bit too. And the viscosity came down a little bit. But I think it was just the extra resolution that really improved the representation.
Great, thank you.
Thanks, Anna. Thanks, Yosuke and Matt. Thank you again, Yosuke, for the talk and for joining us so late in the night. We'll move to our next speaker, Dr. Gary Wick from the Physical Sciences Laboratory, the NOAA Laboratory in Boulder. Dr. Wick is also the chief of the Boundary Layer Observations and Processes Division at NOAA PSL, and has led a lot of work on boundary layer observations, including remote sensing and uncrewed vehicles. Go ahead, Gary.
Right, well,
thanks.
Great. Well, thank you, Aneesh, and thanks for the opportunity to present today. The presentation that I'll be giving here is looking at the ability of satellites, both currently and looking forward, to provide some of these needed observations in this marine boundary layer. And the overall focus here is on the tropical Pacific, but I would say most of what I'm going to be talking about is really much more general and applies to other regions as well. I will say that unfortunately, I was not at the actual workshop myself. I got drawn in terms of the preparation of the paper, but this is an area that I've been, very interested in my entire career. And so this is with respect to a paper that was led by Kyla Dreshka, along with Darren Jackson and Elizabeth Thompson. So I'm happy to be speaking on this. Next slide, please. So as Charlotte mentioned in her introductory remarks, the goal here is really to provide this suite of observations across the whole column, this whole column sampling. And so go from the interface both into the mixed layer on either side of the interface, but then up into the atmospheric boundary layer and the oceanic mixed layer. And so looking in terms of what satellites can do, satellites are extremely good at providing measurements of this interface. But the challenge becomes then trying to go up just above and below the interface, and then also with respect to the resolution and sampling. And so, the satellites have these great strengths, but they're also very limited. And so the graphic on the bottom is out of the paper, and that's just looking at some of these specific variables that we really want to get at and provide observations of. So next slide. So the way that I've structured this presentation is to step through a number of these variables and look at, kind of the current state, future of what satellites can do with that. And so I provided some color coding along the way, kind of a stoplight diagram of how well we do, what our results are with this. And so starting at the interface, start with sea surface temperature, which is, really one of our, best measurements from remote sensing. It's a highly characterized measurement, but even saying that, having said that, the graphic over on the right-hand side shows that it's still a very complicated process, that where satellites provide primarily a measure or information representative of this interfacial temperature, which is highly relevant if we're doing air-sea fluxes and the like. What commonly historically has been desired is often a measurement of a temperature at somewhat deeper depths, which is perhaps more representative of the oceanic heat content. So even with this very well characterized measurement, we have to account for the skin layer cooling at the surface, potential diurnal warming influences below. And so in part because of this range of variables that we're looking at, and also because of the range of sensors out there to do that, there is a broad suite of products with respect to satellite sea surface temperature. And there I specifically call out this group for high resolution sea surface temperature, or GRIST, which has done tremendous work in terms of really providing a common format for the observations. And so, from the blended sort of observations, the OI SST, or the Met Office ocean sea surface temperature, ice analysis, OSTIA down at the bottom, there's many really good products out there. So in terms of correcting for this diurnal warming, or providing information on how much that varies and how these observations may be provided, current analyses often just neglect or only consider observations when there isn't this diurnal warming. But we're making tremendous strides in terms of really correcting and understanding at least the magnitude of this diurnal warming. And so their methods are both through models, which I'll return to later, but also using geostationary satellites. With this continuous sampling, the bottom right, this is a product that I developed where just looking at the time series of observations over the course of the day, we can come up with these amplitude estimates of diurnal warming and see that the magnitudes in many cases can be quite significant and something that we want to take into account. Finally here, speaking in terms of the sea surface salinity, it's a much more challenging retrieval process. It's a less direct measurement, but through Aquarius, SMOS, and various missions, we're actually getting some products that do have very usable accuracy, albeit at somewhat coarser temporal and spatial resolutions. And so the challenge there is really preserving that history of measurements. Next slide. Shifting from the ocean side to just the other side of the interface, we'll look at winds and precipitation. Winds, I would say, is another area where the satellite record is quite good. So we have, extended records of wind speed from passive microwave observations, and then information on the vector direction through scatterometry. And so with these, the basis of the measurement is it's based on the ocean surface roughness. So in the active area, roughness there impacts the returning signal. We change the emissivity. But with that, then rain, anything that has a further influence on the roughening of the surface is a complicating factor. But again, we have quite good records of that. Similarly with precipitation, this has been something that's been studied for a long period of time, both from passive and active sensors. A lot of products are out there that combine the strengths of these. And so CMORPH, iMerge, there are these blended products which provide good information. The challenge with precipitation is something a little bit more with representativeness of, the scale. That precipitation can be very localized, So a broad scale satellite measurement might be quite challenging to capture what's happening in that. And so how do you account for those differences in scale? Also, how do you account for the fine vertical structure of precipitation? So, next slide. Turning back to the ocean side of the interface for a second, we can talk in terms of waves and currents. So with waves, we have reliable methods of inferring something about the significant wave height, primarily from altimetry. But with that, we're missing information more on the directional spectra, the directional structure. And while there are some airborne measurements which allow us to do this, the wide swath radar altimeter, these methods really haven't been extended into the satellite regime at this point. With currents, ocean currents, that's very important for the air-sea interaction, balancing the difference between the wind speed and the currents. It's an area where the efforts to this point have been very, very indirect. And so, they might be derived through a combination of altimetry, which will give geostrophic currents, or looking at cross-image correlations from ocean color, ocean temperature, but again, quite indirect. But this is an area where there's a lot of really interesting work right now, and a new satellite mission proposed called Odyssey, which is based on Doppler scatterometry to give these simultaneous measurements of the wind speed and ocean currents. And so this is being evaluated from airborne measurements out of JPL, a NASA project called S-Mode. And so, some really exciting times to make some significant advances here with respect to the winds and currents. So next slide, please. Now, if we look at across the interface, looking at the heat transfer there, something of tremendous interest that we want, there are a long record of both of satellite-derived heat flux products, both purely observationally driven and through what I'm calling hybrid methods here. And so in the pure observational method, everything is derived from satellite observations. And so this includes work, CFlux, OAPS is a German product, Geofuro out of Japan, but really the most utilized product has been this OA flux out of Woods Hole, Lisan Yu. And so that uses a combination of direct satellite observables and also some reanalysis products. And that comes from the basis of the challenge here is really obtaining the sampling and resolution that we want and getting measurements of the key variables that we need. The method is based on the bulk flux methods, which are indicated with the equations over there on the right, where it's a product of, say, the wind speed and then the air-sea temperature difference or the humidity difference across the interface. And while we've said that the winds and sea surface temperature are something that we do extremely well, the challenge here really comes in with this near surface temperature and humidity. And so that's a work that Darren Jackson, I, among a lot of other people, have worked with over the course of time. We have products out there, but it's a very challenging measurement. It's very indirect. And the graphic at the bottom right is an old graphic. That's from measurements from Paquita Zoidema of humidity profiles. And the issue there is, if you look at the far right, you see an area where it's much drier through the upper atmosphere, moist at the surface. And so a lot of our satellite methods are really ultimately related to the total column measurement. And so as opposed to really providing information on what's happening at the surface, a lot of our measures to this point have been more from subtracting what's happening higher up in the atmosphere and then subtracting that off from the total to get to the surface. So that, kind of speaks to the challenge there. So if we go to the next slide, but there's, excuse me, some very interesting progress in this area where there's plans for a dedicated satellite mission to, first of all, provide simultaneous measurements of all these quantities. So in the past, we've been blending the wind speed, the temperature from various different missions, so that limits our temporal sampling in that. Now we have a proposal to provide simultaneous measurements of all these quantities from the same platform, but particularly going into the passive microwave, something that's very exciting to me is looking at different frequency ranges where we can actually maybe get a little bit closer to those interfacial temperatures and humidity values that we desperately want. So, really hopeful that a mission like this goes forward. Next slide. And then now starting to move a little bit further beneath or above the interface, starting on the ocean side, with respect to the oceanic mix layer, There are products out there directly related to either the mixed layer depth or the oceanic heat content, and these are typically produced through a combination of other variables, blending sea surface temperature, salinity, altimetry. The graphics at the far right kind of illustrate the process here of you can infer something about a mixed layer depth through the combination of the temperature and altimetry, combine that with other information to get a measure of the heat content. And so model-based estimates of this are improving. The other graphic is simulations of this temperature profile. So by combining model information, also blending in Argo profiles, through these blended approaches, we're actually making progress to providing more useful and more thorough, comprehensive measurements across the oceanic mixed layer. So next slide. Then finally, turning to the atmospheric boundary layer, I'm characterizing this as one of our most challenging areas. That the problem here really comes to what extent can we see these layers close to the air-sea interface. And so there's a couple of major methods that we use to infer these observations from hyperspectral regular profiles. The issue is kind of illustrated with the graphic there on the right, where even though we have a lot of different channels, the weighting functions are such that we get information over broader layers, and particularly close to the surface, we don't get a lot of detailed structure right near the air-sea interface. So coming up with this very detailed profile information in the boundary layer is something extremely challenging. An alternate approach that we use here, radio occultation. This is reflected GPS signals, or the signal passes through the atmosphere. It's bent by the atmosphere. That gives us very accurate information on the temperature and humidity structure in the atmosphere, but it's produced over quite coarse layers and coarser resolution. So very useful information, which is great for assimilation into the models, but it's something that doesn't provide a lot of the fine scale structure that we might ideally want for some of these process studies. So with that, next slide. Just to wrap up on some concluding thoughts, as always, satellites, I think, are an essential part of our toolkit. They provide, they're helping us to get towards this comprehensive picture of the air-sea transition zone that we really like. Get good information on the surface. Through blending of multi-sensor observations, some other information, we're gaining the ability to infer more things as we move away from the interface. But challenges remain here, but it's exciting from the prospect that there are a number of new missions being considered and being evaluated that can help us make some great progress in this area going forward. So I will stop with that, and thanks again for your time.
Thank you, Gary. Thanks for a great talk. Any questions for Gary?
Yes, thanks. Very interesting talk. I have a question about the Odyssey mission and the measurement of surface currents. And so you showed earlier, and it's well known, that for the temperature profiles, that there's a very fine scale vertical structure within the ocean mixed layer. And the distinguishing what we're actually measuring is a very key problem. And I'm assuming that the same would occur for the surface currents, that if you're measuring, the upper centimeter, then you're looking at wind-driven signals at swell and waves that are going to be an order of magnitude larger than the mass transporting, heat transporting currents that we know and love. What thickness of the ocean, the upper ocean, do you think the surface currents that Odyssey will measure, what are we actually getting, and how do we interpret that and relate that to the other information about the currents?
Hey, Billy. Yeah, that is a great question. Absolutely true. The challenge is always decoupling these aspects. I have to be fully honest and transparent. I have gone to a number of the presentations on this mission. I have not been too well integrated in. I know that they're really struggling with some of these challenges of even how do you decompose wind currents at the surface, some of the other things. So bottom line, I have to say that I really don't have a good idea of the representativeness there, but I know that that's something that they're really working hard to try and define.
Thanks, Billy. Thanks, Gary. Elizabeth?
Yeah, this is just a further discussion. I don't know if I have an answer to Billy's question, but I wanted to kind of invoke Kyla, who isn't, in this discussion today, but led the article. And I think I always loved how she made these hard problems seem a little bit more approachable and would bite them off. And I think at one conference, she gave a presentation about either the SWAT mission or one of these, satellite innovations. And someone asked, like, that sounds nice, but we're missing all these things. And she was like, well, yeah, it's hard and we could quit now, or we could try and start somewhere. And I think that that's like, just to put Kyla's energy into this, I think that's what she would have said. And she got a laugh from the whole room. And I think it's motivating to attempt these things, even especially of all things, surface current retrievals seem to get everybody riled up, and then you bring in roughness, but I think it's worth trying.
Yeah, absolutely. And I would say from the diurnal warming, an area that, that's something that I probably worked on for 25 some years. And at the beginning, we know we want to include the physics. We were basically breaking even. 20 years later, we're now actually making an improvement by considering the physics, but it's just a long-term process.
Thanks all. Thanks, Elizabeth. Thanks again, Gary, for a really interesting talk. We'll move to our next speaker, Dr. Yassir Eddebbar from Scripps Institution of Oceanography. Dr. Yassir is the lead of the Climate and Ocean Biogeochemical Dynamics group at Scripps. And Yassir has led an NSF project on studying physics and biological, biogeochemical interactions in the tropical Pacific, and also led this article for our climate variations on upwelling and mixing in the equatorial Pacific cold term. Thanks. Take it away, Yassir.
Wonderful. Thank you, Aneesh. And thanks, Charlotte, Aneesh, and Alyssa for putting this together. So this talk is to just kind of summarize the CLIVAR variation articles that we were initially invited to contribute to this issue. This was done in collaboration with Annalena Deppen-Meyer, who is here, I believe, in the audience, as well as Deepak Shirian and Dan Witt. And upwelling and mixing is such a big topic, we decided to maybe focus just on the diabatic component of upwelling, which is associated with mixing, and in this case, turbulent mixing and its biochemical implications. Next, Alyssa. And to kind of motivate our articles, we thought to just kind of take a step back and think about why the cold tongue and mixing and upwelling is so important. This is a region of very intense ocean heat uptake, which modulates air-sea interactions associated with ENSO, as well as has profound impacts on global climate. But upwelling mixing also leads to the upward transport of carbon, which essentially leads to the largest natural outcasting of carbon to the atmosphere. So this is the largest source of natural carbon to the atmosphere. So it's really critical that we understand the processes driving that transport. It's also how nutrients are supplied to the euphotic zone. And in this region, there's intense productivity, which sustains a range of ecosystem processes and dynamics that sustain the lucrative fisheries, including the tuna fisheries that the equatorial Pacific is known for. And this upwelling is also known to sustain the oxygen minimum zones via this enhanced nutrient supply, productivity, and descent of organic carbon, which removes oxygen via microbial consumption at depth. But the upwelling and mixing may also lead to ventilation of oxygen into the thermocline. So it's a bit of a complex process for oxygen. Next. So what makes the equatorial Pacific so important? It's also a dynamically unique regime. This is a region where persistent and strong shear induced by the equatorial undercurrent, which flows towards the east upward, and shears against the south equatorial current, which flows towards the west. Essentially, that shear acts against stratification that's set by solar heating and upwelling of cold waters, and it keeps the flow state near marginal instability just below the mixed layer. So this is a fairly unique dynamical regime in the ocean. And this marginally unstable state is perturbed diurnally via a diurnal cycle in solar irradiance, as well as winds, which act to influence stratification, and shear essentially leads to a descent of a jet that tips the system towards instability, leading to a process known as deep cycle turbulence. And this turbulence, which peaks later in the evening and at night, and then is reduced later in the night and throughout the morning, acts to cool sea surface temperature and induce intense heat fluxes into the thermocline. And even though it acts on small and fast scales, from meters to minutes, it contributes and interacts with a large scale structure, including from diurnal timescales to interannual timescales associated with ENSO. And we thought for this article we were asked to highlight some insight from recent modeling studies and how they might have any implications for the observing systems and process studies. And here I'm sharing this really nice figure put by the TEPEX Science Plan collaborators that shows kind of a visual of this diabatic versus adiabatic upwelling along the equatorial cold tongue, where you get a substantial amount of upwelling just due to the long isothermal flow along the equatorial undercurrent, and a strong component of this upwelling occurs in the central equatorial Pacific via turbulent mixing associated with this shear driven instabilities. Next. So I'm going to do my best not to butcher Annalina's and Deepak and Anna and Dan Witt's contributions, but the third of the upwelling that I've described that's associated with diabatic upwelling is driven primarily by turbulent mixing. This is a nice study by Annalina that shows the cross isothermal flow that leads to cooling of the upper surface layer and warms the thermocline, and the sum of the vertical mixing and solar penetration, or the solar heating of the upper ocean, essentially explains most of this cross isothermal flow. And a nice result that came from these high-resolution simulation studies of POP at 1/10 of a degree is that this cross isothermal flow or diabatic upwelling is very strongly in space and time. So you could see the WCI along 0 degrees in the lower left panel. Is strongly seasonal, so there's very little diabatic upwelling in late winter and spring, and then it accelerates and intensifies in summer and fall when the shear intensifies. And you could also see that it essentially follows or is tightly related to the passage of tropical instability waves shown by the TIV kinetic energy in black dots. It not only varies in space and also it not only varies in time, but it can also vary in space. There's also evidence in the simulations that diabatic upwelling also occurs away from the equator at 3 degrees north. And this was further shown next by a high-resolution simulation with the MIT GCM by Deepak Shirian. The panel to the top shows the downward heat transport in the low Richardson number layer, the high shear layer below the mixed layer, where you see intense heat fluxes going into the ocean, not just at 0 degrees, but all the way up to about 5 degrees north. And that beautiful structure is associated with a range of different processes. We've known that along 0 degrees, variations in the vertical shear of the zonal flow drives quite a bit of the variability in vertical mixing associated with the propagation of tropical stability waves. This nice study by Deepak and colleagues shows that variations in the vertical shear of the meridional flow associated with the anticyclonic flow of tropical stability waves can also push the state towards instability away from the equator. And so, again, it highlights how much mixing varies in space as well as in time. Next. And this was further confirmed by, or reproduced in a way by large eddy simulation experiments led by Dan Witt and colleague a few years ago. The bottom plot shows essentially the maximum downward turbulent buoyancy flux at 0 degrees north and 3 degrees north at 140 west. And you see this is sort of a proxy for turbulent mixing. And the dashed lines in blue and the dashed lines in black show periods of enhanced shear by tropical stability waves that are fed in the model via the boundary conditions. But you see that there's enhanced turbulent mixing during these periods of tropical stability wave propagations, but there's also mixing all the way up to 3 degrees north, and towards the end of the experiment, you see that the mixing at 3 north and 0 degrees is almost the same. So it highlights this the importance of trying to figure out how much mixing actually occurs away from the equator and not just at the equator. Next. So many of these conversations got us also thinking about ocean biogeochemistry. Mixing not only transports heat, but it can also transport biogeochemical tracers, including oxygen, carbon, and nutrients. And so we hypothesized that this spatiotemporal variability in turbulence also drives variability in these biogeochemical tracers. These panels to the right show the snapshot in an ocean physical and biogeochemically coupled model in POP 0.1 degree that shows the air sea flux of oxygen, positive or red, into the ocean. The contours show the SSTs, and that shows, and they contour the tropical stability waves in the model. And then the middle and lower panel show the downward mixing flux of oxygen and the mixing flux conversions, with the orange lines showing regions of high shear-driven turbulence contoured by low Richardson number regions. And what you notice is as these tropical stability waves pass through, you get intense mixing flux of oxygen into the thermocline with the conversions essentially showing depositing of oxygen in the upper thermocline. Next. So although that mixing is intermittent and its tends to be associated with variations in the shear as well as variations in the wind, it integrates over time to become the main dominant source of oxygen supply in the upper ocean, somewhere between 50 and 120 meters. It even dominates over the supply of oxygen via lateral advection by the equatorial undercurrent and the meridional cells, and acts to supply oxygen that's removed by microbial consumption and upwelling at depth. So this is critical for the mean state as well as variability of oxygen ventilation. Then next. And this is also important for chlorophyll. We've long seen these beautiful cusps of tropical stability waves in the equatorial Pacific. But so far, we don't fully understand what drives these cusps of chlorophyll, and eddy and turbulent mixing likely have an influence over that biological productivity, and it potentially may have potential feedbacks on ocean physics via suppressing the penetration depth of solar radiance, increasing stratification, and potentially reducing vertical mixing. And I encourage you to read this paper by Chan et al. that describes some of these processes. Next. So to wrap up, we thought to end on some open questions. Some of the main questions we've been thinking of is, how does turbulent mixing influence the vertical exchange of nutrients, carbon, and oxygen in the real ocean? Most studies have been model-based, and what are feedbacks that might arise from these exchanges of nutrients, carbon, and oxygen? So the simultaneous supply of nutrients and carbon might lead to both outgassing of carbon as well as the biological removal of carbon. So there's some important feedbacks that we need to understand. And finally, how do small-scale processes influence the large-scale structure and variability of these tracers on various timescales? And just to wrap up on the last slide, we concluded with some implications for the observing networks and proposed process studies. Most observations of mixing were done at 0 degrees and 140 west. So there's a need to test the meridional and temporal variations of mixing predicted by these models and by geochemical consequences with sustained observations. And we proposed or supported the expansion of higher frequency in space and time measurements of turbulence and biogeochemistry along the equator as part of the TPOS renovation, as well as the need for more process studies to characterize the full 3D circulation associated with TIVs and their interactions with mixing via the growing fleets of autonomous vehicles that can sample these processes. And with that, I'll open it for questions.
Thanks very much, Yassir. Fantastic talk. Any questions for Yassir this time? Maybe while we wait, Yassir, I had one question somewhat related to the previous talk from Gary as well about how atmospheric boundary layer processes coupled to the ocean boundary layer processes, right? And some of that talk was on the physical side of the coupling of the atmospheric boundary layer processes and oceanic boundary layer processes. Could you also speak to the biogeochemical side? I know there are potentially biogeochemical aerosol productions like DMS or other aerosols that can outgas and then lead to potentially clouds with CCNs that then have an impact on the ocean surface, right? And the thermodynamics and dynamics of the ocean surface. Do you have like other thoughts of coupled ocean atmosphere processes that impact biogeochemistry as well?
Yeah, it's a good question, and a bit the aerosol part is outside my wheelhouse, so I'm not gonna dive too far in there. But yeah, these upwelling and mixing processes and their impact on productivity is gonna have an influence on the fluxes of various aerosols and their impact on the boundary layer. I would say, as far as other coupled VGC processes, one is that the cold tongue is a region of potentially intense outgassing of nitrous oxide, which is a powerful greenhouse gas that's produced in the boundaries of the oxygen minimum zones. And it's a gas that's really hard to measure because it equilibrates fast and outgasses really quickly. And so as oxygen minimum zones expand or shrink, the amount of nitrous oxide that is produced and outgassed might be changing, and it might feed back on climate, perhaps on longer timescales, but it's still an interesting feedback. And I think process studies might, shipboard measurements of nitrous oxide are probably really needed to quantify the variability of nitrous oxide outgassing along that region. Yeah, as far as other feedbacks, I think the other main one is the variability of chlorophyll associated with tropical instability waves and mixing, and how that influences the penetration of solar irradiance and ocean dynamics later on. But that one is also fairly poorly observed and understood. Yeah.
Great. Thanks, Yassir. I don't see other hands raised at this time. So great. We'll move to our next speaker. Thanks again, Yassir, for a fantastic talk. And if there are other questions for Yassir, please feel free to post them on the chat. Sorry. Our next speaker is Dr. Elizabeth Thompson from the Physical Sciences Laboratory of NOAA in Boulder. Elizabeth is also the marine lead for the Boundary Layer Observations and Processes Division at the PSL NOAA lab. Elizabeth has participated and led many field campaigns, has a really broad interest in observing the air-sea transition zone as well as clouds, precipitation, and related processes. Thanks, Elizabeth, for leading this article in the Variations and for presenting today.
Thanks. And I would comment that I was happy to say that for TPEX, just to add on to Yassir's great presentation, that we were working with, should TPEX still happen, we've worked out a way to make nitrogen and various species of measurements on the ship in the equatorial upwelling zone. So that would help out that process. That was kind of an add-on that we got to the physical measurements. So I'm passionate about observations and using them to improve models and understanding. And so my colleagues and I kind of did a collection to highlight and advertise the usage of the in situ tropical Pacific observing system and in the operational sense. And so this was a complement to the article that Gary presented about. And so I just want to thank the co-authors. Next slide, please. So we mainly focus on the operational observing system that's often referred to as the GOOS, Global Operational Observing System. We focus on routine, operational, and/or long-term time series, and we focused on physical, oceanographic, meteorological, and the air-sea interface. The field campaign data archive and location and availability vary experiment to experiment, and so we didn't necessarily discuss that here, but you'll see me kind of fit in where research plays a large role in sustaining the operational observing system. And so this is sort of a table of how we organized our thoughts from through the ocean at the interface, and then some observations in situ into the atmosphere. And what I want to relay really is that we have very few data measurements, and so all of them are incredibly important. Next slide, please. We begin to understand the tropical Pacific operational observing system from great collective reports like the TPOS 2020. And so I think learning about this, it's really helpful if for anyone interested in this to go through the extreme amount of effort that went into documenting where we are. And a lot of that still applies. Maps like this are often the first entry point to understanding this. You can see the different dots that demonstrate that document, you know, the different types of data that go into everything we know about the ocean and every way that we're trying to inform the downstream weather and climate predictions and the studies of how the ocean circulation is evolving in this coupled system. And then what the presentation is going to do is go through all these dots basically. Next, please. One of the most foundational and like backbone of our operational observing system are Argo floats. These are floats all over the world, but you can see some data voids in the Arctic and specifically in the maritime continent related to difficulties of the floats to reach there and these currents and coastlines that are kind of dynamic for them. But for the most part, the goal of this program to have a certain number per degree grid box was reached. They reach the surface every 9 days in between drifting at 1 to 2 kilometers, and they make temperature and salinity vertical profiles during every ascent and descent. And sometimes in research efforts, that same platform can be used to measure the sound associated with rain rate and wind speed. And I checked, there's 4,119 floats as of yesterday. And when I made this, there were like 3,900 in 2021 when we put it in. And so they've been trying to maintain this 4,000 amount. So next slide, please. The other, I think, often forgotten backbone of the observing system are XBTs, so expendable thermographs, and then the aircraft deployable one, AXBTs. There are about 20,000 vertical profiles of just ocean temperature made from this, yay large device. It's launched off the side of ships or dropped from aircraft. It represents 15% of the global ocean observing system. And what they did is they identified key ship tracks over which we must make XBT measurements. And this is led on both science ships and commercial ships that everyone is kind of working toward doing this. And this effort to collect and serve this data is provided by NOAA AOML, the lab in Miami. Next, please. The TOW or Triton moorings are the tropical Pacific moored arrays. This is a prior version of this. These sites were originally designed to monitor ENSO back in the 90s, and it's a very long-standing array that's now taken care of by NDBC, but it was started at PMEL. And the issue is that you'd be hard-pressed to find a continuous record of any one air, sea, or ocean variable. It's very difficult to maintain. But some research efforts have added on to these. And so I just want to note, in addition to the operational data available from these and served, I think here is a screenshot of what you can get to download the data at PMEL, is that ocean turbulence has also been collected for a large part of the last decade by moored mixing meters at 140 and 0. And that was led by Oregon State. And then the next slide, we're going to go into how this array has been evolving since the TPON workshop. Next slide, please. So the TOW array is getting upgraded it's already begun, and it will continue through 2026. This is just a near equatorial detail of the array. The green squares are all of the near equatorial sites that are getting recapitalized, as is to say, we're using capital that the Weather Service and others invested in the array to make it more operational, in the sense that all instruments that were intended to be on the site will be on there, and plus some new ones. And then the other detail to add is that the light green circles around on the equator at 175 east, 175 west, 140 west, and about 110 have ADCPs. And then all along the cold tongue, there will be ADCPs. And this was drawn out of the TPUS 2020 recommendation that we have to learn more about the vertical current structure on the ocean. And the really big thing is that these will be near real-time reporting. Though those currents are not going to be assimilated into the GTS, they will be used for near real-time analysis, which modeling centers use to say, how are we doing with regard to ENSO? So this is a major advancement. All of these buoys getting upgraded, and particularly the addition of the ADCPs. Next, please. So the top panel is the TPUS 2020 proposal for additions and changes. And then just to say, when you return to these slides, you can see at least as of October 2024, this is how NDBC planned to implement. One thing to note is that we've lost the capacity via collaboration or otherwise logistical for anyone to maintain, as of the details that we know now, the moorings west of 160 east. And the other thing is that some sites have been dropped because they're like off the equator, some sites have been dropped, much to the chagrin of some people, but the rationale was that, like, say at 10 north, satellites do a very good job of measuring the winds, and the conditions are like meridionally similar, and we'd be better off if we highly sampled the equator, where satellites have a harder job resolving, let's say, gradients in wind, and also more densely capture vertical gradients near the surface. And so a lot went into this over the last 5 years, and a lot of people thought really hard about this, and I think we're going in a really good direction, and NDBC is a critical partner for this within the Weather Service arm of NOAA. Next, please. With regard to the surface mooring changes and the subsurface changes in the moored arrays, if you just focus on the left here, these slides were provided by Billy Kessler. The standard TAO, as it exists, had a not so dense, about 20 meter apart temperature sensors, and for the surface mooring, it had wind, air temperature, and relative humidity. The recapitalized sites will be fully flux capable in the bulk and radiative sense, and this is a huge advancement. So they'll add the solar and long wave radiation, barometric pressure, and rain rate. They used to have rain rate on some, but like very few had a capable rain rate measurement by this time. And then we've added shallow currents on some, that's to the right here. We've added more dense sampling within the ocean mixed layer, particularly near the surface, with 5 meter sampling and the addition of some salinity measurements. And then in regard to this right side, there used to be ADCPs, but they were offset from the standard mooring. And this was due to sensor issues at the time, but there's been an effort to combine the regular ocean mooring with the ADCP. We figured that out. Billy Kessler and Megan Cronin figured that out, how to moor the ADCPs looking up and down and not disturb the data with the other sensors. And so the recapitalized integrated ADCP mooring has everything we already talked about, and currents will measure all the way up to about 7 meters. And that's a major advancement with what we thought would be possible. And they go down past most of the thermocline details. So next, please. And I'll try to go quickly through the rest of these. There's a lot of reference material. These moorings at, let's say, 7 or 8 different sites, funded mostly by GOMO, but also contributed by NSF and other NOAA grants. These ocean reference sites, or ocean site moorings, are really redundant research quality measurements in climate sensitive regions like the stratocumulus regime or the Kuroshio extension region. And they provide like 3 sensors of everything, and they get turned around every year. And just to highlight that some of these are some of the longest continuous locations of measurements in the ocean in the world. Some have been dating back to the 1950s, and even the ones starting in 2000 are incredibly important for long-term measurements. Next, please. The Ghost Ship repeat cruises are very important for our global ocean observing system. There are specific lines that are repeated for vertical profiles of temperature, salinity, conductivity, pressure, currents, and ocean carbon data and oxygen that are taken with the ship CTD. And these are largely funded by GOMO. Next, please. I wanted to highlight a few research to operational-ish observation. This is a really long time series of repeat glider transects in the Solomon Sea, so the far western Pacific. It's at the entry point of the Indonesian through flow, where currents are very strong, and the pileup of mean sea level pressure is important for triggering or understanding ENSO. And so a few researchers from PMEL and Scripps, funded by GOMO, have been maintained this time series every year from 2007 all the way to 2020. So this is a very important data set because it's one of the only public maritime continent data sets that we have. Next, please. I wanted to highlight the Florida State University effort supported by GOMO to collect all NOAA UNOLS and research ship cruise data. So every time the ship is out, it's collecting data. And that is actually being reported automatically to this repository You can go to this site through Samos, and they've been QCing the data. It's all ship specific. And they also recently imported all of my team's like 60 to 90 cruises. And that's what our map shown here, but it also includes all NOAA and UNOL ships. So it's a great database to use. Next, please. The Global Surface Drifter Array is maintained by NOAA AOML. These are largely just SST and sea level pressure and some ocean surface wave height and direction data. So they're all over. You can see it's difficult to keep these near the equator. We have to keep resupplying at the equator, and they're drogued. So along with making these surface measurements, the position is used to derive some ocean current information. Next, please. There are, in terms of the Pacific, there are a few significant wave height, wave period, wave direction, and SST buoys called CDIP wave buoys. There are some along the West Coast, Hawaii, American Samoa, and in the South Pacific. And so these are some of our important wave information data in the Pacific. Next, please. There are also tide gauges from NOAA. It's very hard to add other meteorological measurements to these. It's a simple data set, but it is important. And it's of note that this has been going on for over 150 years. Next. The NDBC National Data Buoy Center surface stations and mooring site shows basically everything that I just talked about all in one site. It archives them. You can kind of see the large breadth all the way up to the extratropics. Next, please. Sail drones, though not routine or operational, sail drone missions have been completed about every year in some capacity by NOAA, PMEL, and AOML since about 2017, funded by a variety of NOAA grants. And so you can find their data online that either in the tropical Pacific, across the whole thing, and as highly advertised or publicized the Atlantic hurricane season. These have unique bulk and direct flux capability, as well as near surface meteorological ocean and some ADCP measurements. Next, please. And lastly, there are repositories of radiosonde data. So this is some of our only data we have above a typical buoy or sail drone height of 3 meters off the sea surface or 8 meters off the sea surface. Radiosondes are launched all over island and coastal and land locations. Brendan Wolding has looked into all of this a lot, and so if you're ever interested in this database, please take a look at his papers. This data set is maintained by NOAA and CEI. There's also radiosondes in the form of dropsondes released by the NOAA aircraft every year as part of hurricane or mid-latitude experiments. And I would note that about every year someone emails me asking if anybody has compiled all of the sondes from all of the ship field campaigns. And so there's a lot of interest for that, but there's no known data set of or archive of that. Next, please. So just some wrap-up thoughts. I was really interested in compiling all this information. What I found is it's maintained by individual people often at both NOAA and universities, largely through the research line office of NOAA, either in the form of program funds or lab support. And this is both a strength. It's like incredible what people have done and for how long they've been doing it. But it's also a vulnerability in that there's a need for succession plans and sustained support. There's also the rising cost of ship costs and Iridium costs. Iridium is the network that transmits data to satellite, from the sea surface to satellite and to our data centers. And this threatens how much science we can get done while we're still maintaining these observing arrays. And that there are still areas we haven't been able to routinely monitor or are difficult to maintain, but are crucial for our understanding and predictive capability. And so there's still effort to work more in the Arctic, maritime continent, equator, and then the western and eastern boundary currents. That's all I have.
Thank you, Elizabeth. Great talk. Any questions for Elizabeth? I had one, Elizabeth, while we wait for others. In terms of the timing of the field campaign and what the Pacific state would be right now, could you speak to how long a lead time would you be thinking of in terms of deployment of resources, what forecasts would be useful in terms of like seasonal to subseasonal timescale that would help like decide where you go in for deployment, and what observations to take in case we are in a El Nino pattern or a neutral or a negative ENSO phase.
For TPEX in particular, or
For TPEX, yeah, sorry, for TPEX field campaign more.
I think the ENSO field, like the ENSO state, is very important to keep track of in those forecasts, and it's something that we're kind of weighing in a cost-benefit analysis of. I think also like just a financial forecast would be probably most helpful for us right now. Like we're most hindered by our inability to plan with certainty at NOAA right now, but we have come up with like several scenarios. Like if we have this much money and the ENSO state is this, and if we have this much money in this fiscal year. And so I think that the more the community can come help us create such matrices of what's most important and what's most critical to fund as a group, so as to make a sum greater than the parts. Like we really welcome input, and I would just say from the field campaign planning perspective, like all those things are being taken into account, and we'd love more people to help us with that. We don't have like a forum for that right now, other than like, please funnel things through the TPOS monthly meetings.
Great, thanks, Elizabeth.
Yeah, thanks for that great overview, presentation and update. On the Western Pacific for the Institute moorings, there was indication that we were looking for non-US support for that part of the array. Are there prospects for having deployments in the Western Pacific, and how important will that be for future operational forecasting?
Do you mean in terms of the moored array?
The moored array.
I wonder if Billy or Megan can speak on that if they're still online. I think it's like we don't know everything, and we like particularly those Western sites like had a lot of international collaboration. Like they depend on something, and I don't remember the exact details, but I know Megan or Billy could probably speak to it.
I see Megan and Billy online. Billy, yeah, go ahead.
Okay, thanks, Elizabeth. So the real answer is we don't know. It seems not too likely that any collaborator is willing to make the kind of commitment to a moored array that requires a lot of ship time to maintain. So there could be some opportunities, for instance, during TPEX, to have ships that would deploy moorings for limited periods of time. But I don't think that, I like to be optimistic, but it seems unlikely that we're going to have a sustained array the way we had with the Triton maintained by Jamstec. So, really the challenge to me is what, in the absence of moored arrays, can we use our autonomous assets? So I'm thinking of sail drones and wave gliders, especially, that would sample the ocean mix layer and the air-sea fluxes and the bottom of the atmosphere. And in some ways, in the Western Pacific, those are the most important. Whereas in the East, the thermocline and the undercurrent are really important foci. In the West, a lot of it is happening within a few meters of the few tens of meters, say, of the surface, and that could be sampled by these autonomous assets. And so, there's a need for careful thought about how you would do that and what the scales, both the spatial and temporal scales that are needed. And then there's a question of finding money. But that does seem like potentially we could get a lot of the information that we need, even in the absence of a sustained moored array.
Yeah, and the way that GOMO sees the tropical Pacific observing system, like they view uncrewed systems as a key part of filling in between moorings or visiting these other places. So that's not, I wouldn't say that's just like a pipe dream. That's something that they're considering at a
systems. Our technology is rapidly evolving, and in fact, just in April at the last observation coordination group that oversees the GOOS, the Global Ocean Observing System, the network of uncrewed surface vehicles was endorsed as being a GOOS network, and that group is rapidly coming together, and we actually have a new name. It's Sunfleet, and anyway, there's lots of possible technology solutions to the Western Pacific, and partnerships forming, and so it'll be an interesting time moving forward. But it is possible that we can fill in that big hole in the West, and it's a matter of exactly what is needed, and then solutions can be found.
All right, thank you. Yeah, thanks for ending us on an optimistic note, Megan. It's amazing to see the progress that has taken place over just the last few years since this workshop. I want to thank everyone for attending, and a special thanks to our presenters, and again to the US CLIVAR office for helping us put together this webinar series. I want to remind everyone that this was part one. Part two of this webinar series, which will last for 1 hour, will be held on June 3rd from 11 a.m. Eastern time.